Hi there! In the previous videos we saw how we could estimate the parameters in a linear relation between two variables. However, it's not difficult to see that this is not the whole story. Indeed, it seems very likely that mortality is not only determined by the calcium content in the tap water. So, very often we will need to consider more than one independent variable. Let's take a look at a situation where this will be the case. Here you see a few lines of a rather large dataset. It contains information on 5,454 cars. All of these cars are Ford Focuses. You see the second-hand price for each of these cars, together with a few of their properties: the age, the engine size, the type of transmission, the mileage, the fuel type. Okay, imagine you're a car salesperson. Then you may be interested in how each of those variables influence the car's second-hand price. Well, let's investigate this. Let's build the model as we did in the mortality example. In the same way as before, capital Y is our dependent variable, the one we will be trying to predict. Here yi is the price of car number I. We model yi again as an intercept, plus a coefficient times our first variable, say the age of the car. Notice that we no longer work with alpha and beta, but rather with beta 0 and beta 1, since that makes it easier to add more terms later on. We also want to include the engine size and the mileage in our model. So we add another term, beta 2 times x2i, where x2i is the engine size of car number I, and a term beta 3 times x3i, where x3i is the mileage of car number I. As you can see, we can now add any number of variables. So, in general, a linear regression model using p explanatory variables will look like this. If p is greater than 1, we call this multiple linear regression, as opposed to the simple linear regression we covered in the previous videos. However, the two remaining variables, fuel type and transmission type, look quite different. They are not quantitative, but rather categorical. The fuel type is either diesel or petrol, and the transmission type is either automatic, manual, or semi-automatic. So, how can we use these in our model? Well, we will deal with these variables by introducing so-called dummy variables. Let's introduce x4, which is 0 if the fuel type is diesel, and 1 if the fuel type is petrol. And let's add this to our model. We get an extra term, beta 4 times x4i. In this way, the fitted price for a petrol car will contain a term beta 4 hat times 1, whereas the fitted price for a diesel car will contain a term beta 4 hat times 0, which is 0. Hence, the fitted price for a petrol car will be just beta 4 hat units higher than the fitted price for a diesel car, for which all other variables are the same. Alternatively, you can interpret this as having a different intercept for petrol cars and for diesel cars, beta 0 plus beta 4 and only beta 0 respectively. Intuitively, you might think that the transmission variable can be tackled in the same way, by having a dummy variable, take the values 0 for automatic, 1 for manual, and 2 for semi-automatic. This would lead to the following models for each transmission type. However, this does not work. In this way, the predicted price for a manually shifting car would be beta 5 hat units higher than for an automatically shifting one, and the same increase would be visible from manual to semi-automatic. However, there is no reason that these two increases should be the same. The solution to this is to work with two dummy variables. x5 is 1 if the transmission is manual, else it is 0. And x6 is 1 if the transmission is semi-automatic, else it is 0. This leads to the following three situations. Summarizing, x5 and x6 are either both 0 for automatic transmission, or 1 and 0 respectively for manual transmission, or 0 and 1 respectively for semi-automatic transmission. In our example, for the transmission variable, we had 3 possible outcomes, also called levels, and we needed 2 dummy variables. And for the fuel type, we had 2 levels, diesel and petrol, and we needed 1 dummy variable. Well, you always need 1 fewer dummy variable than the number of levels for a categorical variable. So another categorical variable with 4 levels would lead to these 3 dummy variables. One of the levels then corresponds to all these dummies being 0, and this is called the base level. It does not matter which one you choose for this. For each of the other levels, always exactly one of the variables is equal to 1, and the other ones are 0. Okay, we now have our model. It contains 6 explanatory variables, 3 quantitative ones and 3 dummy ones. To fit this model in R, we do not need to define those dummy variables by ourselves. But for the interpretation afterwards, it's important to understand that this is what is being done. The R command lm is the same as in the case of simple linear regression, but now we make clear that there are several explanatory variables separated by plus signs. Summary looks good. All variables seem to contribute significantly to the model, reflected by the observation that the null hypothesis beta equals 0 gets rejected for each of the variables. Moreover, the R squared is quite high. Notice that the program R by default chooses the levels in alphabetical order. So for the transmission, automatic was base level. The coefficient estimate on the line transmission manual is then indeed the estimate for what we just called beta 5. And in fact, all parameters in the output are in the same order as in our model. However, we should not forget to check our model assumptions. And unfortunately, here things do not look very nice. This is the QQ plot for the residuals. At the right-hand side of this plot, there is quite a large deviation from the straight line. And the scatter plot of the residuals reveals that quite a lot is going on. First off, notice the negative fitted values. A negative predicted price, that seems very odd. And also, for these cars, the residuals is always positive. Well, obviously, the price in the dataset is positive, so it is always larger than the predicted negative price. So there is clearly a trend in the residuals. Finally, the variance of the residuals seems larger at the right than at the left. Here we have this heteroscedasticity. All of this leads to 2 main questions. What causes this behavior and how can we solve it? Well, common sense will tell you that the mileage will have an effect on the price. The higher the mileage, the lower the price. However, an increase in mileage from 1000 to 1500 probably should have a larger impact than an increase from 10,000 to 10,500. Rather, it seems plausible that each doubling of the mileage has the same effect on the price. The function that captures this behavior is a logarithm, since the logarithm of 2x is the same as log 2 plus log x. So maybe a better model is obtained by including the logarithm of the mileage x3 rather than x3 itself. And similarly for the age of the car, x1. By the way, this is still called a linear regression model, despite the logarithmic functions in it. The linearity refers to the way the beta parameters appear. Let's look at the R output for this new model, which we called fit2. The scatter plot for the residuals looks much better now, no more pattern, and the assumption of constant variance seems reasonable. The QQ plot still shows a small undesired behavior at the tail ends, but let's leave it at that for now and keep this as our final model for this example. In our final video on linear regression, we will look at how you can decide exactly which variables to incorporate or not in your model. But before we do that, let's look at the R summary of this model. There is still one line in the output that we haven't touched upon, and yet it seems familiar. since it contains a test statistic and a p-value. It is indeed a hypothesis test. We already saw the t-tests whether the individual beta parameters were zero according to the null hypothesis. Well, now we have a test to check whether all of the parameters beta 1, beta 2 and so on are zero. Can you interpret what the null hypothesis claims? Indeed, if all those parameters are zero, then only y equals beta 0 plus an error term remains. So all cars then get the same price prediction, and none of our explanatory variables has any significant influence on the price. If this H null is true, then our model is utterly worthless. Well, fortunately, this null hypothesis gets rejected by a convincingly low p-value. The test statistic has a Fisher distribution, hence the name f-test. We will not bother you with what such a distribution looks like or with any of the mathematical background, so we wrap up this example here and focus our attention on the exercises and on the next video. So, see you there!